Here's a problem that shows up everywhere you simulate the real world: a cell, a circuit, a drug moving through a body. The system has two clocks. One thing changes in an instant, another drifts for hours. And that gap, fast next to slow, can bring a simulation to its knees. Speed up the obvious way, and the whole thing blows apart. The way out has been sitting in a kitchen the whole time. Picture a thick steak going into a hot pan. The surface reacts in seconds, it browns, it chars. The center barely notices for the better part of an hour. Same piece of meat, two completely different clocks. A fast surface and a slow core. Hold onto that, it's the whole story. Strip the system to its simplest piece, one quantity relaxing toward rest. Y prime equals lambda y. That lambda, the eigenvalue, the number that sets how fast a mode settles, is the mode's clock rate. A big negative lambda is the surface. It races to equilibrium. A small negative lambda is the core. It ambles. A real model has many at once, the eigenvalues of the system's Jacobian, the map of how every slope shifts. And here's the definition that matters. Stiffness is the ratio, the fastest rate divided by the slowest. When that ratio is huge, the system is stiff, not big, not complicated. Two clocks, far apart. So you're impatient, fair enough. You crank the burner to high to push the core along. You come back, and the outside is charcoal, while the inside is still raw. The fast part couldn't take the big push. Turn it down, nudge it gently, flip it every minute, and now you're babysitting a slow core through 1,000 tiny moves. That's the trap. Here's the standard move. In math, to step forward, read the slope where you are now, and follow it, the explicit method. Forward Euler. On our mode, y next equals 1 plus h lambda times y. The step h multiplies the rate. Watch the fast surface mode. Take too big a step, and the tangent overshoots the curve past equilibrium. To the other side, larger than before. Step again, it overshoots harder. The numbers don't settle, they explode. To stay stable, the size of 1 plus h lambda has to stay below 1, which for the fast mode means h can be at most 2 divided by L2, divided by the fastest rate. And that's the cruelty. The fastest mode, the one you don't even care about, sets the largest step you're allowed. Long after the surface is done, you're still creeping for stability, not accuracy, babysitting the slow core. Now the other kitchen. No pan. A water bath, held at exactly the temperature you want the center to reach a perfect medium rare. You drop the steak in, and you walk away. An hour, 2 hours, it doesn't matter. The meat can never overshoot the water. It just arrives. You didn't cook toward the answer, nudging and checking. You set the answer, and let everything settle into it. That bath is an implicit method, backward Euler. The change is almost too small to see, and it changes everything. Explicit reads the slope where you are. Implicit reads the slope where you're going at the destination, and finds the step consistent with it. Y next equals y now, plus h times f, evaluated at y next. The unknown sits on both sides. The answer is defined by itself. Solve it for our mode. Y next equals y now, divided by 1 minus h lambda. Its amplification, the factor per step, is 1, divided by 1 minus h lambda. And for any decaying mode, that factor is below 1 for every step size. Every one, a microsecond or an hour, it stays stable. This is astability, unconditional. The step is finally free, governed by how accurately you want the slow core, and nothing else. You set the bath and walk away. 2 steaks on the board. 1 ruined, 1 perfect, same meat, same target, 2 methods. And the honest question isn't which one. It's why one of them is safe, no matter how big a step you take, and the other never can be. The answer isn't about meat at all. To see it, we have to leave the kitchen. Here's the picture the kitchen can't draw. Take the step times the rate h lambda, and plot it as a point on a plane. The complex plane. Every mode of every problem lands somewhere. Our decaying modes all sit on the left side. Now shade the region where a method stays stable, where its amplification is below 1. For the explicit method, that safe region is a small, bounded disk. The fast surface mode, pushed far out to the left, falls outside it unless you shrink the step to drag it back in. That's the crawl, drawn as geometry. For the implicit method, the safe region is the entire left half, the whole side, where things decay. Every decaying mode is inside, always, and out at the far edge. The amplification doesn't just stay below when it goes to 0. The stiffest mode is crushed in a single step. That's L stability. And one last thing, not a tuning knob. A while, no explicit method, ever, can fill that whole half plane. Its amplification is a polynomial, so far out it must blow up, and its safe region stays bounded. If you need unconditional stability, you need an implicit step. The bath was never optional. But sous-vide isn't free. You need the gear, the bath, the patience. Each step buys you safety, and you pay for it. A pan is cheap and instant. The bath is deliberate and slow. So which do you reach for? That depends entirely on the state. Reading the slope at the destination has a price. The unknown is on both sides, so each step you have to solve for it, usually with Newton's method, which needs the Jacobian, the matrix of how every slope shifts, and a linear solve, every step. An explicit step is nearly free. An implicit step is real work. So it's a trade. Explicit takes many cheap steps. Implicit takes few expensive ones. For a stiff problem, that trade is a landslide. A handful of big stable steps beats millions of tiny ones, easily. For a non-stiff problem, where the clocks are close, the cheap explicit step wins, and the bath is overkill. That's the whole decision. Stiff fast next to slow reach for implicit. It's exactly why a pharmacokinetic model with fast absorption and slow elimination, or a chemical network, calls a stiff solver the L soda, and sous-vide says your tools fall back to. Same idea every time. When the clocks split, cook to the answer. One method, drawn as threads. The two clocks fast surface, slow core, stiffness. The big step the fast clock forbids. The explicit limit, 2 divided by L. The slope read at the destination. The implicit step, stable for any h. The map that proves it, the left half plane, and the wall that keeps explicit methods out. And the bill, a Jacobian and a solve. Every step, 5 threads, 1 pot. Stiffness was never about size, it's a gap between clocks. And the fix isn't to chase the fast one with ever smaller steps. It's to stop chasing, set the destination, and let the system settle into it. Decide the doneness, then cook to the answer. But the bath only ever promised one thing. The steak can't overshoot. Not that it's done. Stable at any step size isn't the same as accurate at any step size. So the real question was never whether it blows up. It's this: how big a step can you take before the answer quietly drifts from the truth?